Hello everyone. So in this module, I'm going to go over enthalpy in a little bit more detail and the change of enthalpy. And I want to discuss bond breaking and bond forming. After this module, we will go ahead and continue to move to the coffee cup calorimeter. Now, with bond breaking and bond forming, let's take a look by looking at a chemical reaction of what's going on. So I have hydrogen gas, chlorine gas, and that's going to form HCl. And overall, this is going to be an exothermic reaction. So this is going to be an exothermic reaction. So let's take this in steps. So first, what's going to happen is I have some HH bonds and some Cl-Cl bonds. And in order to break these bonds, so I'm going to go ahead and break these. When you break bonds, just like if we were to try to break a piece of wood ourselves, we need energy to break that piece of wood. So these bonds, they need to absorb energy to break those bonds. So to break bonds, we need to absorb energy. Now, if we absorb energy, that is going to be called endothermic, right? So we talked about that before, kind of endothermic, you absorb energy, and you guys have been hearing about that for a while. So when we break these bonds, those bonds absorb energy, and that bond breaking is endothermic. So what happens next is that we'll have, once we break these bonds, we're going to have an intermediate stage where we have, so we're kind of having this intermediate stage, and we're going to have some H's and Cl's kind of floating around. And what happens is if they get close enough and it's energetically favorable, these hydrogens and chlorines, they're going to snap together. And what's going to happen is energy is going to be released. So when we form bonds, energy is released. And if energy is released, we say it is exothermic. So that step in the reaction is exothermic. Now, these two energies, the endo and the exo, can be different magnitudes. And depending on which one is greater, the overall reaction will it will either release energy or gain energy based on which ones are higher in magnitude. So in ours, we took a look at this and said, okay, this one is exothermic. It's going to be releasing energy. So if it releases energy, the exo portion, or the forming bonds portion, it must have been greater in magnitude than endo for it overall to be an exothermic reaction. Well, how can I explain this? I'm going to use what's called a potential energy diagram. So a potential energy diagram. So in a potential energy diagram, we are going to look at the change in enthalpy, and those are our energy changes. So I'm going to start out here by making an arrow here, and this is our potential energy, and it increases as we're going up. And what we're going to start with is we're going to start with our reactants. So in our example, we have H2 and Cl2. Now, I've already talked about the hydrogen chlorine. In order to break those bonds, it has to absorb energy, right? So if we absorb energy, how we're going to denote that is you draw an arrow going up in this direction. So this is going to be indicative of our bonds being broken. And earlier, I talked about an intermediate stage. This is where all they're floating around before they snap together. And here, once they do snap together, what's going to happen? As I indicated in our last example, the magnitude here must have been larger. So that means if we're releasing energy, we must be going in the other direction in this energy diagram. So here you're gaining energy if you're going up, you're losing the energy if you're going down. So here you're losing the energy. This is when we form bonds. We're going to be forming bonds. So it's going to end up here with our HCl's over here. So we have our products. Now, this diagram hopefully explains what I've been talking about earlier. So this exo part is larger than our endo part. So the magnitude of the whole thing, because we're looking at a change in enthalpy, right? This has to be a bigger number than that number for it to be exothermic. Okay, so now this potential energy diagram shows this intermediate stage. Well, most of the time, I just did that to explain what was happening, but most of the time, they don't look like that. They actually look like this. So here are two potential energy diagrams. On the left, here we've got our exothermic reaction. So this is our exo. So in this one, we know that heat is released to our surroundings. And all that's cut out of there were the intermediates. As you can see, the reactants, our H2 and Cl2 are still here, and here's our HCl. Now, the only thing I want to point out is don't worry, well, not the only thing, don't worry about the activation energy here. You'll learn about that in Chem 401. What concerns us is this arrow right here. Notice this dotted line here and here. This difference is our delta H. This is our delta H. So our delta H, our final minus initial here, will be a negative value. So our exothermic reactions are going to be when our delta H is less than 0. Okay, so our heat is being released to our surroundings. Now, let's look at the opposite. Let's look at our endothermic diagram, potential energy diagram. Here, our system, so here we have that it absorbs heat. It absorbs heat from the surroundings. It absorbs heat from the surroundings. So our energy then to break our bonds has to be greater than forming our products. So here's our energy absorbed. So energy absorbed overall then has to be positive. Okay, so the energy then to absorb, to break those bonds must have been greater. So just the opposite of the diagram I showed earlier. Now for you guys just to have a table, and exothermic and endothermic, exothermic's negative. Heat flows out of the reaction into the surrounding. It feels hot. Endothermic's the opposite. It's a positive value. Heat flows into the reaction from the surroundings and it feels cold. Okay, well now we'll be moving on to the next module. Don't forget after this to take your quiz. Okay, bye.